This is the second video on section 5.5, absolute extrema. And here we're going to finish the example that we started in the previous video. And recall that our function gxy is x cubed y plus 3x squared plus y. We want to find the maximum and minimum values of g on the region bounded by this triangle. And so we have 0, 0, 1, 0, and 1, 1. In the previous video, we looked at this part of the boundary, where x is between 0 and 1 and y is 0. Case 2, we're going to look at the vertical line, x equal to 1 and y is between 0 and 1. So g of 1y, so x will always be 1 along that line. So g of 1y is going to be y plus 3 plus y. So we have 2y plus 3 is g of 1y. This is a line. It has its as y goes from 0 to 1, it has its minimum value of 3 at 0. And when y is 1, it has its maximum value of 5. And so g of 1, 0 is equal to 3, and g of 1, 1 is equal to 5. These are the min and max values of g along this line. Case 3, we're going to look at the slanted line, y equals x. So in this case, x ranges from 0 to 1, and y is equal to x. So we're going to look at g of xx, which is x to the 4th plus 3x squared plus x, because we are looking at g of xx. Now, we're going to look at this in terms of a real valued function that we might have studied in Calculus 1. So let's define h from 0, 1, because that's where x goes. X is between 0 and 1. So we have h from 0, 1 into r. H of x is defined as x to the 4th plus 3x squared plus x. Now we want to find the max and min values of h on the closed interval 0, 1. So we calculate h's derivative, 4x cubed plus 6x plus 1. And we'll notice that that is always positive on 0, 1. So if x is between 0 and 1, this derivative is always positive. So h does not have any critical numbers between 0 and 1. We'll test h's endpoints. H of 0 is 0, h of 1 is 5. Now, h of 0 equal to 0 corresponds to g of 0, 0 is equal to 0. H of 1 equal to 5 corresponds to g of 1, 1 is equal to 5. Now we put all three of our cases together. The smallest value that we found was 0, and we found that at 0, 0. The largest value we found was 5, and we found that at 1, 1. Now, what you've probably noticed is our cases overlapped. We found the 0 and we found the 5 in more than one case. And that's because when we look at our boundary here, we tested the corner points twice, right? Because the origin was part of case 1 and case 3. This point was part of case 1 and case 2. And this point was part of case 1 and case 3. And this point was part of case 2 and case 3. So our corner points for our region appeared in two different cases. And so they got considered more than once. There is there's not a theorem that says that our max and min have to occur at the corner points of our region. But because of the way, because of this special example, it happened that way. But in general, we do not necessarily have to have our max and our min at the corner points.